In this tutorial we're looking at section 12.2, which is on continuous random variables and probability functions. Okay, continuous random variables can have any value within a given range. Okay, our intervals are used since values can be anything, so often we'll say, like the example they use actually in the textbook is nose lengths. Now the length of your nose could actually be anything, okay, but they have ranges such as 27.5 to 32.5 millimeters and 32.5 to 37.5 millimeters, etc., because we could literally have any number in between there. Okay, probability density functions. Okay, these are used to represent continuous random variables. The area under a probability density function is always equal to 1, since the sum of our probabilities is equal to 1. So the idea there is that we have an integral from a to b of f of x dx equals 1. If that occurs, then we can say that this function f of x between these two terminals can represent a probability density function. F of x always has to be greater than or equal to 0, okay, because we know that we can't have negative probabilities, okay, and that's for all our x's between a and b. Now, f of x could be less than 0 if it's outside the domain of a and b, because that doesn't matter. We only care about the domain from a to b. And look, our domain could be all real numbers. Okay? The probability that c is less than x is less than d, well, we just integrate from c to d f of x dx. Okay, where c to d would be somewhere in between a and b. The probability that x equals 0. Okay, where x is an element of a to b. So what we mean by that, okay, is it's quite surprising, but with continuous random variables, okay, our probability of being any actual value is actually 0, because there's actually an infinite number of possibilities that you could get. Okay, the probability of getting any distinct actual value is 0. So it's a little bit different. So what that really means, though, okay, is that we're really going to be talking about times where we want to know when the probability that x is greater than or less than some value or between certain values. Okay, are the type of questions that we look at with these. Now, the probability that a is less than x is less than b is equal to the probability that a is less than or equal to x less than b, which is equal to the probability that a is less than x is less than or equal to b, which is equal to the probability that a is less than or equal to x is less than or equal to b, and that all of those equal the integral from a to b of f of x dx. The probability that x is less than c is equal to the probability that's less than or equal to c, which is equal to the integral from a to c f of x dx, where x is an element of a to b and c is somewhere between our values of a and b. Now, our probability density functions are written as piecewise functions, okay, when the function has a domain less than r. Okay, and so what it looks like is something like this. Okay, where we say f of x is our function. So say in this case, just 2 outside of x take 1, where x is between 1 and 2. Okay, you just need to put this other little part, which is saying that f of x is equal to 0 everywhere else. Okay, and that just ensures that all we're talking about is this part up here. Okay, and then everywhere else we're not caring about whatsoever. So we'll get into some worked examples. Okay, so worked example 1. Okay, what we need to do is sketch a graph of each of the following functions and state whether the function is a probability density function. Okay, so the first one here, we've got f of x equals the one that we had just a minute ago, 2 outside of x take 1, where x is between 1 and 2 and 0 elsewhere. So when we draw that, okay, what we get is we find that goes through 1, okay, goes up to 2 and across to 2. Okay. And then at 0, everywhere else. Okay. And we're looking at this part here. Okay, so we need to look, okay, is f of x always positive? Okay, well it is, yeah, so that's fine. Okay, well we need to also see whether the area under it equals 1. Okay, well we could just think it's a triangle, so a half times base times height. So we get our half times our 1 times 2, which equals 1. Okay, so it's always positive. The area under is equal to 1. So yes, this function f of x could be a probability density function. Okay. For the next one, what we look at is we've got f of x equals 0.5 between 2 and 4 and 0 everywhere else. So if we're to draw that, go to our axes. Okay. We've got 2, we've got 4, we've got 0.5. What we're saying is we've got a graph like this and 0 everywhere else. Okay, and we're looking at this area under here. Okay, so it's always positive, tick, so we're fine there. We look at our area. Okay, well it's 2 times 0.5, which equals 1. Okay, so the area under it does equal 1, so we're okay. When we have a look at the at number C, or part C, our function is 2e to the negative x between 0 and 2. Okay, so when we graph this, okay, we start up here at 2, okay, and we come down to 2. Okay, and our endpoint is actually 2 and e to the, no, sorry, 2 and 2 on e squared. Okay, is our endpoint. Okay, no, it looks a little bit funny, but that's what we've got. Okay, so if we look, we're always positive, so that's fine. Okay, when we integrate this, well, we need to integrate from 0 to 2 of 2e to the negative x dx. Okay, so that means that we get negative 2 e to the negative x. Okay, from 0 to 2. Okay, which means we get negative 2e to the negative 2. Okay, plus 2e to the 0. Okay, and when we do that, we find that we get 1.7293. Now clearly that doesn't equal 1. Okay, so C would not be a probability density function. Okay, what we can have in these cases is something like, okay, so that might be the first bit. Okay, show you that it can't be a probability density function. Okay, and what they'll do is say, okay, well, there's some value k for which this area would equal 1. Okay, so it would be a probability density function. So it could be, if f of x is a probability density function, okay, they'd say, which has the equation 2e to the negative x, from 0 is less than x is less than k, and 0 elsewhere, find k, that type of thing. Okay, so we'll be integrating and setting it equal to 1. Okay, and we'll have a bit of a look at worked example 2, which is similar to along the lines that I was just talking about, but not quite. Okay, so we've got our two functions. So we're told that given their function below are probability density functions, find the value of a for each function. Okay, so that means that for this one, we've got f of x equals a outside of x take 1 squared from 0 to 4 and 0 elsewhere. Okay, so what we do is we need to integrate, okay, from 0 to 4 of a outside of x minus 1 squared dx, and that equals 1. Okay, so we bring this a out the front, integrate from 0 to 4, x minus 1 squared equals 1. Okay, so when we do that, we get a outside of our x minus 1 cubed, okay, on 3 from 0 to 4 equals 1. Okay, so when we sub our values in, okay, we get a outside of, well, going to be 4 minus 1 is 3, so 3 cubed on 3, okay, minus, well, be negative 1 cubed on 3 equals 1. So we get a outside of 9 plus a third equals 1. So A times 28 on 3 equals 1. Okay, so that means that A is going to be 3 on 28. Okay, so just going through integrating it based on that. Okay, for this one, we've got f of x is equal to a e to the negative 4x for x is greater than 0, and it'll be 0 elsewhere. Okay, so what we need to do for this one is we need to integrate from 0 to infinity, okay, of a e to the negative 4x dx and set equal to 1. Okay, so we can bring our a out front again. E to the negative 4x dx equals 1. Okay, so now what we need to do is we need to do our a times the limit as k approaches infinity of 0 to k e to the negative 4x dx equals 1. Okay, it might have been a little while since you'd done any integration involving infinities, but remember we need to substitute our k in. Okay, so then we need to go through our a times the limit as k approaches infinity. Okay, well we're going to be negative 1 on 4 e to the negative 4x. Okay, from 0 to k was 1. Okay, so we've got to sub in our k value. Which means we're going to get negative e to the negative 4k on 4 plus a quarter is 1. Yeah, and then what we can do is we can rearrange this a little bit, make it a times the limit as k approaches infinity of minus 1 on 4e to the 4k plus a quarter equals 1. And the reason why we need to do that is because now we need to look at this, okay, and go, well, what happens as k approaches, sorry, that should be infinity, as k approaches infinity? Well, as this gets really, really, really big, we're going 1 divided by a really, really big number, means we get a really, really small number, and we say that's 0. So we say we get a outside at 0 plus a quarter equals 1. A or a on 4 equals 1. Okay, so a is going to equal 4. Okay, so it might have been a little bit of time since you've seen ones like this, so make sure if you're having a bit of trouble, go back and have a look at that in the section on integration. But look, otherwise, that's all we've got for this video. Okay, so hopefully you won't have too much trouble with these questions. I mean, you can always use your calculator to help you out at times with some of your integration. Okay, that's no problem with a lot of these questions. Okay, so hopefully you can get through the questions without too much trouble.